In this presentation, we explore the modeling of entanglements in polymer chains using a soft, coarse-grained approach called the slip-link, slip-spring, or SLSP model. Entanglements in polymer melts are crucial as they affect the mechanical and dynamical properties of materials, such as viscosity and elasticity. Understanding these entanglements near interfaces like liquid-vapor boundaries is especially important for applications in coatings, adhesives, and microfluidics. Traditional models like the Kremer-Grest KG model capture entanglements explicitly but require fine atomistic detail and are computationally expensive. The SLSP model introduces topological constraints via slip springs connecting polymer chains, allowing a coarse-grained but realistic representation of entanglements. This approach is combined with the many-body dissipative particle dynamics (MDPD) method, which models non-bonded interactions and explicitly represents liquid-vapor interfaces. Here, the authors investigate how well the SLSP model replicates static and dynamic entanglement properties near interfaces by comparing it with the KG model. Additionally, the work applies these models to study the dynamics of filament breakup between plates, a process relevant to rheological measurements. Figure 1 provides a schematic view of the SLSP model near a liquid-vapor interface, integrating the many-body dissipative particle dynamics or MDPD non-bonded interactions. In the diagram, polymer chains are illustrated with color differentiation, where the blue chain is connected to neighboring black chains via slip springs. These slip springs represent topological constraints that simulate entanglements by linking different chains dynamically. Importantly, the vapor phase adjacent to the liquid does not impose any additional topological constraints, effectively reflecting the contour or shape of the polymer chains at the interface. This design allows the model to capture the influence of the liquid-vapor boundary on chain entanglements without artificially restricting chain motion in the vapor region. The approach merges the realistic non-bonded interactions offered by the MDPD framework with a representation of polymer entanglements that are computationally efficient yet topologically meaningful. This figure forms the foundation for subsequent analysis of how entanglements behave near interfaces in a coarse-grained simulation setting. Figure 2 highlights the importance of separating dynamic and static properties during the top-down coarse graining process. This separation allows independent tuning of these properties in the SLSP model and its related frameworks. To model interactions with a substrate, the authors introduce a Lennard-Jones-type wall potential, where the interaction depends on the distance between particles and the wall. Parameters such as the energy strength and cutoff distances are carefully set to enable realistic wall-particle interactions. The use of the many-body dissipative particle dynamics (MDPD) model, rather than the more typical dissipative particle dynamics (DPD) model, is crucial as it ensures realistic particle packing near interfaces and compensates for the missing neighbor effect that can arise close to surfaces. Importantly, this compensation is not strictly necessary but improves the physical fidelity. The density profiles for liquid-vapor interfaces obtained with this model are smooth and flat, lacking density peaks close to the interface, which aligns with the high coarse graining level of MDPD. Additionally, when varying the degree of entanglement as controlled by the fugacity parameter, the model demonstrates consistent density profiles near both liquid-vapor and wall-liquid interfaces, especially when the compensating potential is included. Without this potential, the interface's position and shape and particle arrangements near the wall are disrupted, producing undesired artifacts. This figure thus underscores the compensating potential's critical role in maintaining realistic interfacial structures during coarse-grained simulation of entangled polymers. Figure 3 compares the concentration profiles of slip springs in the SLSP model and kinks in the primitive paths of Kremer-Grest KG chains near a liquid-vapor interface. The profiles were obtained using the Z1+ algorithm, which identifies entanglement points in polymer melts. Both profiles were shifted and normalized to align with density and chain end density profiles for clarity. Notably, the density of both kinks and slip springs remains approximately flat in the bulk region away from the interface. However, close to the interface, there is a slight decline in their density. This decrease is attributed to the fact that chains residing near the interface have fewer neighboring chains to entangle with, as the vapor phase does not contain polymer chains. Additionally, an enrichment of chain ends near the interface appears in both models, reflecting the decreased entanglement opportunities at boundaries. The qualitative agreement between the SLSP and KG models in these static entanglement features suggests that the SLSP combined with NDPD successfully preserves the fundamental nature of polymer entanglements near interfaces. The authors interpret this as validation that static entanglement properties are accurately captured by the coarse-grained SLSP model in the proximity of interfaces. Figure 4 illustrates the temporal evolution of a polymer filament or stalk confined between two plates modeled by the Kremer-Grest KG description. The figure shows 6 snapshots, starting with the initial stalk formation in panel A, progressing through linearly thinning stages in panels B through E, and culminating in an exponential decay phase illustrated in panel F. Each snapshot displays 2 views. On the left, the polymer particles are rendered to show the filament structure explicitly, while on the right, the particles become partially transparent to emphasize the chain entanglements, which appear in red. In the KG model, entanglements correspond to kinks identified by the Z1+ algorithm. Observing these images, one can see how entanglements are distributed and evolve as the filament thins and eventually breaks. This visual progression captures the dynamics from an initial relatively thick filament to a final thin neck undergoing an exponential thinning process, reflecting the physical mechanisms controlling filament breakup. The authors interpret this sequence as an illustration of how entanglements manifest and influence polymer filament dynamics in a fine-grained model. Figure 5 parallels Figure 4 by depicting the time evolution of the polymer filament between two plates, but here using the SLSP model description. Like before, 6 panels illustrate the progression from initial stalk formation through successive thinning stages to the ultimate exponential decay phase. Each snapshot again provides a 2-part view. The left side shows the polymer particles explicitly, while the right side renders the particles transparent to emphasize entanglements, which in the SLSP model correspond to slip-spring bonds visualized in red. This figure demonstrates that the SLSP model captures the filament thinning and breakup dynamics, qualitatively similar to the KG model. Visualizing the entanglements as slip springs reveals how these topological constraints evolve and influence the thinning filament structured between the plates. Overall, the authors present this figure to show that the SLSP model not only reproduces the static entanglement features, but also dynamically captures the essential behavior during filament breakup, supporting its utility as a coarse-grained tool for rheological studies. Figure 6 presents the quantitative comparison of rim neck size evolution during capillary breakup, CABR, of a polymer meniscus, as simulated by both the KG and the SLSP models. The neck radius is plotted as a function of time. The blue curve corresponds to the KG model, while the red curve shows the SLSP results. Both models reproduce the characteristic breakup regimes predicted by theoretical descriptions and observed experimentally. Initially, the neck radius decays linearly with time, as emphasized in the inset, consistent with classical theory where viscous forces dominate. The KG model's radius decreases somewhat faster than the SLSP models, likely reflecting small differences in surface tension, which were not explicitly matched during simulations. As the neck size shrinks below a certain molecular scale, entanglement dynamics govern the filament's response, leading to a terminal exponential decay regime seen in both models. Relaxation times extracted from fitting these exponential decays are very similar, with the SLSP model's entanglement time approximately 1.19 times 10 to the power of 4 LJ time units, and the KG models about 1.27 times 10 to the power of 4. This remarkable quantitative agreement indicates that the SLSP model, integrated with the MDPD liquid vapor representation, can faithfully reproduce the complex rheological dynamics of entangled polymers including in processes involving interfaces and breakup. The authors interpret these results as strong validation of the SLSP approach for simulating nano-rheological processes and interpreting experimental measurements. In conclusion, the authors have presented a comprehensive study demonstrating that the slip-link-slip-spring SLSP model, when combined with the many-body dissipative particle dynamics (MDPD) approach, effectively captures both static and dynamic entanglement properties of polymer melts near liquid-vapor interfaces. By validating against the detailed Kremer-Grest model, the SLSP framework is shown to preserve key features such as the distribution of entanglement points and chain end enrichment near interfaces. Furthermore, during filament thinning and breakup scenarios, the SLSP model reproduces the characteristic dynamical regimes observed in KG simulations, including linear neck thinning, followed by entanglement-controlled exponential decay. Quantitatively close relaxation times suggest that this coarse-grained approach enables accurate rheological predictions while requiring substantially less computational effort. The inclusion of realistic liquid-vapor interfaces via MDPD, along with compensating potentials to ensure artifact-free density profiles near substrates, further enhances physical fidelity. Altogether, this study supports the use of the SLSP plus MDPD framework as a powerful and efficient tool for simulating polymer entanglement dynamics in complex interfacial environments. This opens avenues for studying nanorheology, capillary breakup rheometry, and interpreting experimental observations in technologically relevant systems.